Okay. So, before we get started on all 111 slides, no worries.
See how many slides there are for this one?
Yeah, I printed
Two
them
things
out.
to go
Adding
over. One,
notes.
the lab for Thursday is not posted yet. I will get it up today. I just got it yesterday. I don't like it, and I'm trying to figure out what to do with it. Okay? I'll have something up.
A and then just take the rest of the semester off.
So I told somebody before, what's probably going to happen is we're going to show up, we're going to do some of it, the part that I think is useful, and then we will go to the classroom next door and start doing the slides that we didn't finish today. Okay?
I should just give you my
The
number.
department is desperately looking for people to be tutors for human nutrition and microbiology. If anyone did well in either of those classes, let me know. And if you're interested in being a tutor, let me know. I have no idea how much you pay. If you're interested, let me know. Whatever. I was grading the homework over the weekend, and I noticed some things that kind of concerned me. I think it's a one-time deal just based on the material. So it was no secret that the quiz last week on the naming had the lowest grade. And everyone kind of agreed that they saw that coming. When I was grading the homework, I saw some things that made it very clear that a number of people were Googling things. Okay? I didn't mark it wrong, but you saw what happened if you Google things and you didn't learn what you were actually doing, and then you took a quiz when you couldn't Google things. Okay? It's pretty.
That's why we should
It's pretty easy for me to tell you Googled it when you write something, an element with the British spelling. there were five or six people that did that. Okay. And also there was a molecular compound with prefixes, and the one in the book, the compound in the book isn't something that actually exists in nature. And so when you searched on it on Google, you found a compound that had those same two elements, but had nothing to do with the prefixes listed in the book. Okay? It was diphosphorus pentoxide. And in nature, the combination of phosphorus and oxygen like that is P4O10. Okay? Which is not what the prefixes said. Okay? So it was obvious people were Googling it. Okay? Naming is about the easiest thing to Google, right? It says your name, write the formula, you Google the name, you write the formula, and it spits out. If you want, it gives you a formula and you want the name, you put in the formula, and you write down the name it gives you. From here on out, things aren't going to be that easy to Google. So I don't think that's going to be a problem, but just keep it in mind that you're not doing yourself a favor, okay? Getting a quiz wrong on the quiz, getting a question wrong on the quiz is worth a whole lot more than getting letter D wrong on a homework problem. Okay. And the last thing, I'm not getting a whole lot of questions emailed to me. Don't hesitate, okay? If you have questions, email me, not Google.
So, like you said, the diphosphorus oxide.
I think it was diphosphorus pentoxide or something.
Oh,
They fix it? They give you-
but it wouldn't be.
No. So what is the molecular formula for diphosphorus pentoxide? P2O5. Just go by what the question says. So, right. But so today's lecture is really long. We're not going to finish it. Okay. Not even going to attempt to finish it. We're just going to go along and see how far we get. Okay. So the last couple couple weeks, we talked about compounds as a whole, naming what a compound is, things like that, ionic, molecular. Last week we talked about kind of the atomic scale of a compound with ionic bonding, and covalent bonding, Lewis structures, shapes, things like that. Now we're going to get into sort of, at the beginning of this lecture, the numbers that go along with compounds. And then at the end, which we may or may not get today, we start to look at chemical reactions. Okay. So the title of this is chemical composition. Okay. That title more or less only applies to the first part of it when we start talking about numbers. Okay. First thing is we can talk about percent composition of compounds. Okay. And so what this is if you have a sample, say I give you a 50-gram sample, and one way or another, you figure out that in that 50-gram sample, there's 10 grams of carbon. Okay? All this does is figure out what percentage of that sample is carbon, which would be 10 divided by 50. Okay? The mass of the element, our oxygen, the mass of our carbon is 10 grams and divided by the mass of sample, which is 50. So all you're doing is just a very simple percent calculation of what percent of your entire sample is the element you're looking for. Okay. So here is an example. We have chalcopyrite, it's a mineral, and our entire sample is 3.67 grams, and it has this number of grams of 3 different elements. And the question asks, what is the mass percent for each element? So if I wanted to find the mass percent of copper, how would I do that?
1.12 over 3.67.
Copper. Let's see. 1.27 grams
Oh,
divided by my total mass,
3.67
3.67 grams times 100 equals 34.6%. Okay. So if I wanted to find percent iron, how would I do that?
same thing, put the 1.12
1.12 divided by 3.67
times 100.
grams times 100 equals 30.5. 30.5%, and this is copper, that's iron, and then sulfur, 1.28 divided by 3.67 times 100 equals what? 34.9. So 34.9%. Okay? And that's all there is to it. Okay? You may come across a problem where you have to use the fact that they all have to add up to 100%. Okay? Or say if you had a 3.67 gram sample and they gave you grams of copper, grams of iron, you can figure out how many grams of sulfur you have, right? Because they have to add up to 3.67. Okay? So just because they don't directly give you all of the information doesn't mean you can't solve for it very easily. So, just like I said, remember, everything has to add up to 100. It's a good way to check your math. See if everything adds up to 100. If it doesn't, something's wrong.
I got 100.4.
Yeah, Ben.
What if it's rounding up to slightly more than 100 because it had to round?
Usually what would happen is if you rounded one of them up, the way the math would work, you'd end up rounding one of the other ones down, and it would cancel. If you got 100.1 or 99.9, don't worry about it. So, if I had my 50 gram, my 3.67 gram sample of chalcopyrite is this percent of each element. If I had a different chunk of chalcopyrite, would the percentages be different?
No.
No. Chalcopyrite is chalcopyrite. The sulfur, copper, and iron are always in these ratios. Okay? So this is just like the density, which a lot of people got wrong on the post lab. If you cut something in half, density does not change. The mass gets cut in half and the volume gets cut in half. So the density doesn't change. Okay? So, if you had a 100-gram sample of chalcopyrite, how many grams of copper would you have? 34.6. You have 100 gram total, 34.6% of that is copper. Because it's 100 grams, the math is easy. Percentage just becomes grams. Does everybody see that? Okay. If I had a 50 gram sample, how many grams of iron would I have?
15.2.
Half of that, 15.25. So you just take that percentage and multiply it by how many grams. Another one. We have a copper compound. We don't know what it is. We know it's a compound that has copper in it. It weighs 1.63 grams, and of that, 1.30 grams is copper. We know the only other thing in there is oxygen. So it's not given how much oxygen there is. And so the question says, what is the percent composition of this compound? So where would you start?
You will start by, yeah, 1.30 over 1.63.
So you got 1.30 grams divided by 1.63 grams
Times 100.
times 100 equals 79.8%, and that is copper.
And then you just subtract that from 100.
Right. So for oxygen, you take 100 minus 79.8 equals 20.2% oxygen. What's another way you could have gone about this math?
33 grams over 163.
Yes. So you could have said the whole thing has to weigh 101.63 grams, and 1.30 grams of that is copper, which means you have to have 0.33 grams of oxygen, and then you could do the division times 100 again. This is less math. They both come out the same place. Does this make sense? I think this is the last slide on this. So, speak now or forever hold your peace.
So the ratio is always going to be the same?
The ratio of the percents from one piece to another piece, no matter how big it is, how small it is, it's going to be the same. Okay? If you had one molecule of this compound, the percentages would be the same. Okay. Let's talk about the mole. The mole is not complicated unless you make it complicated. Okay? It's one of those things that is going to seem really weird until the light bulb goes off in your head, and then you're going to say, oh my God, why was that so hard for the last week? Okay? A mole is just a way of counting things. Use it like a dozen, okay? If a dozen, if If I say I have a dozen eggs, how many eggs do I have? 12. A dozen is a way to count. Just like if I say I have a pair of eggs, how many eggs do I have?
2.
2. I can count in pairs. I can say I have 5 pairs. And you know immediately how many I have. That's 10. If I say I have 2 dozen, you immediately know how many I have. 24, right? A mole works the same exact way. It's just a really weird number, okay? So this is the official mascot of the American Chemical Society. There's a guy in there, or a woman, I don't know. There's a person in there, I assume. But it walks around, so I assume there's a person in there. But it's a giant mole with a lab coat and goggles. Okay. We can count eggs. We can't count molecules, okay? So what we need to do is we need to count sets of molecules so that combined is big enough for us to count, okay? Imagine an egg was too small for us to count, but a dozen eggs was large enough for us to count. If I counted 3 dozen, even though I couldn't count individual eggs, I know there are 36 of them there, okay? So a mole is a quantity that's big enough for us to measure, for us to see. A molecule is not, okay? A mole, just like a dozen is 12 and a pair is 2, a mole is 6.022 times 10 to the 23rd. Like I said, it's a really weird number. You're just going to have to memorize that, okay? There's no ifs, ands, or buts. There's no way you can figure that out on a quiz or an exam. Yes, hold on.
What's the word particle in relation to the word molecule or atom?
So, very good question. So, a mole, you can use moles to count anything. You can count a mole of people. You can count a mole of tables. You can count a mole of molecules. You can count a mole of atoms. Okay? Think of this word as a thing. Okay? No matter what you count it. You say I have 2 moles of tables. Okay? The table is the particle. Okay? It's a thing. Okay? And this is called Avogadro's number. Avogadro was the one who figured out what this is. Okay? And is there anyone here that has ever been a checker at a grocery store? Someone last year thought it was funny. She said she knew avocado's number because just the little number on the sticker for the avocados. So she knew avocado's number, which was a lot shorter and easier to remember than Avogadro's number. So 1 mole of carbon atoms is 6.022 times 10 to the 23rd atoms. A mole of H2S molecules is 6.022 times 10 to the 23rd H2S molecules. A mole of copper 1 oxide is 6.022 times 10 to the 23rd copper 1 oxide. We call them molecules. I don't know if you talked about this, don't worry about it. But ionic compounds aren't technically molecules, we call them formula units. Don't worry about it. Okay. And you can also have a mole of moles. If you had 6.022 times 10 to the 23rd little things digging in your yard, that is a mole of moles. Okay? Does anyone read the cartoon online XKCD?
Yep.
There's 1. So it's kind of a nerd comic. I read it, so I'm not meaning that in sort of negative connotation. But so there's comics, and the guy that does it also has this series of what if. Sort of those weird questions. You say, what if this happened? He actually does the physics and the chemistry and everything to figure out what if that happened. Okay. The last one I saw was, what if a pitcher threw a baseball at the speed of light? And it ended with the end of the universe. Right. So if you have a mole of moles, that many moles crammed together is actually about the size of the moon, okay? So a mole, we've never seen a mole, an actual rodent, it's not very big, it's about that big, right? And so if you put 6.022 times 10 to the 23rd of them together, the gravity of them would form them into a sphere, just like a planet, and it would be about the same size as the moon,
A
okay?
lot of moles.
It's a lot of moles. That's a lot of moles. But a mole of water molecules is about that much. So that tells you how small that water molecule actually is, right? If 6.022 times 10 to the 23rd of these is the size of the moon, and that same number of water molecules is this big, those water molecules have to be really, really small. So the mole, we say it's a way for us to think about the microscopic world in our own world, okay? If the water molecules are that small, we can't count them. But if we count how many of these we have, and multiply it by 6.022 times 10 to the 23rd, we actually do know how many water molecules we have. The way this was originally discovered, it was set. It was set. This is a mole. And what that is how many atoms of carbon-12, that means the isotope of carbon that has a mass number of 12, that's 6 protons, 6 neutrons. So if you had all carbon-12, it would take 6.022 times 10 to the 23rd atoms of it to weigh 12 grams. Okay? And what that means is that these atomic masses up here are also molar masses that we'll see. Okay? So if I give you 12 grams of carbon-12, you have 6.022 times 10 to the 23rd atoms in your hand. Okay? This is what a mole looks like. Okay? It's hard to see, but there is carbon, that's graphite there, that's black. But they're not all that big, right? But they're big enough for us to be tangible to us. That's something we can relate to. We can measure that, we can see it, we can feel it, and then we can just use that conversion factor to figure out how many molecules or atoms we have. What really tripped some people up last semester was going between moles of molecules to moles of atoms. Okay? If you have a dozen molecules of H2S, how many atoms are in each H2S molecule? 3. There are 2 hydrogen atoms and 1 sulfur atom. So if I have 1 dozen H2S molecules, how many atoms do I have? 36. 3 dozen. Okay? That didn't seem that hard, right? Don't make it any harder when we switch to moles. If I have 3 moles of H2S molecules, how many moles of atoms do I have? 3. Right? If I have 1 dozen, I have 1 dozen molecules, I have 3 dozen atoms. If I have 1 mole of molecules, I have 3 moles of molecules. Okay? So how many sulfur?
Yeah, I don't get it.
Did I say something wrong?
Yeah, we just don't get it.
Yeah.
You lost me.
You said molecules twice instead of the second time saying atoms.
If you have, let's do it again. If you have 1 dozen molecules of H2S,
Okay.
you have 3 dozen atoms total. Yeah,
How do you know we have a dozen molecules?
I'm just saying.
Oh, okay.
If you have a dozen
Okay,
molecules,
gotcha.
you have 3 dozen atoms.
Okay.
If you have 1 mole of molecules, you have 3 moles of atoms.
Say that last part one more time.
If you have 1
Uh-huh.
mole
Of that.
of molecules, you have 3 moles of atoms, because there are 3 atoms for every molecule, if you were to break that up into atoms. Okay? So if I have 1 mole of H2S, how many sulfur atoms do I have?
1.
1 what?
1 mole.
1 mole. For every molecule, you get 1 sulfur atom, right? Which means if I have 1 mole of molecules, I have 1 mole of sulfur atoms. If I had 1 dozen molecules of H2S, in them there are 12 sulfur atoms, right? There's 1 sulfur atom for every molecule. Okay? So this is actually asking how many sulfur atoms, not in moles, but an actual number of atoms. How many is that? Right. So we said there's 1 mole of sulfur atoms, and 1 mole is 6.022 times 10 to the 23rd. Right. There's one mole of sulfur atoms for every mole of H2S molecules. Okay? If I have 1 mole of H2S, how many hydrogen atoms are there?
2.
There are 2 moles. If I wanted to figure out a number, how would I do that? Yes. So it's 6.022 times 10 to the 23rd times 2. Okay? So if it's number of hydrogen atoms, we have 2 moles times 6.022 times 10 to the 23rd equals 12.044 times 10 to the 23rd, but that's not correct scientific notation, because this number has to be between 1 and 10. So this becomes 1.2044 times 10 to the 24th. I imagine there are some more examples coming. Okay. Like I said, a mole of carbon-12 weighs exactly 12 grams. Like we said, this number not only is the average mass of an atom in AMUs, is also the average mass of a mole of it in grams. So if I had a mole of hydrogen atoms, how many grams would it weigh? 1.0079, basically 1, all right? That number, if you have 6.022 times 10 to the 23rd of them, that number becomes how many grams you have, okay? Let's see, carbon, oh, that's not carbon. There's an easy one from that. Let's do argon. Argon, let's say it's 40. It's 39.98. Do easy math, say it's 40. Okay? If I have half a mole of argon atoms, how much does it weigh? 20 grams. If I have 2 moles of argon atoms, how much does it weigh?
80.
80. Okay? You can use that to multiply. If you have half a mole, take 0.5, multiply it by that. If you have 2 moles, take 2, multiply it by that. The units, when we're using this in terms of moles, are grams per mole. The unit makes sense. If I have, that's the same, for every mole that I have this many grams. For every mole of carbon, I have 12.01 grams. Grams per mole. Yeah. For molecules, you you add it up just like you were calculating atomic mass or molecular weight. So for CO2, you just go the mass of carbon times plus 2 times the mass of oxygen is 44.01 grams per mole. For every mole of CO2 you have, it weighs 44.01 grams. It's the same exact math you've been doing, it's just a different unit and it means something slightly different. Instead of talking at the atomic scale, we're talking at the gram scale where we can see it and feel it. What is the atomic mass of hydrogen? 1. What's the molar mass of hydrogen? 1 gram per mole. What's the atomic mass of oxygen?
16.
16. So what's the molar mass of oxygen? 16. Let's do water. Atomic mass of a water molecule. 18. What's the molar mass of the water? 18. What are the units on atomic mass? AMUs. What's the unit on molar mass? Grams per mole. Okay? Same number, different unit. Because there's different unit, it means something slightly different. If you're going to calculate this calcium chloride, how would you find the atomic mass of it?
Calcium. So. Yeah.
So you've got calcium. How many calciums are there? There are. There's 1 times the mass. Calcium. Yeah, let's call it 40. 40. Then there's chlorine. How many chlorines are there? 2. Don't miss that. This 2 means there's 2 of these, so there's 2 chlorines. And the mass of chlorine is 34.5. How many oxygens are there? There's 6. There's 3 from each one of these units, and there are 2 units. 2 times 3 is 6, and oxygen is 16. So you would multiply these, 40, you got 69, right?
Yes.
And then
96.
6 times 16
96,
is 96.
and it all equals 205.
Oh, thank you. So the atomic mass of calcium chlorate is 205 AMUs, and the molar mass is 205 grams per mole. Make sense? You've already done
Is that
this.
the easiest way to like write it out, like if you have a long one, you write down each
That-
element and then how many there are of those?
That's how I do it.
Just like a math, like any other math problem. I just started in parentheses and worked my way out.
Oh, okay.
So I multiplied it by 3 and
Yeah.
then added
It's
CO2
exactly,
multiplied it by
it's just
2
like
and CA.
if you had, during math, and you had a parentheses with a 2 outside of it, that 2 gets multiplied by everything inside, just like you were saying.
So you did it.
Okay.
I just started because I worked my way
So,
out.
what contains the greatest number of atoms? A mole of copper, or a mole of gold? I heard gold, I heard the same. It's the same. A mole is a mole. The question, where's the greatest number of atoms? Here you have 6.022 times 10 to the 23rd atoms of copper. Here you have 6.022 times 10 to the 23rd atoms of gold. The number of atoms is the same. What has more? What has more atoms? A gram of copper or a gram of gold? I heard copper and I heard gold. Why copper?
Copper's less dense than gold.
worried about density.
They have less mass. Copper has less mass, like the less amount of mass than the whole thing.
So the molar mass of copper is 63.5. The molar mass of gold is 197. Okay? Do I have more moles of copper or more moles of gold if I have a gram of each?
More copper.
I have more moles of copper because a mole of copper weighs less. A mole of copper weighs less. So if I have the same mass of each one, let's think of it this way. If I have a gram of feathers and a gram of rocks, do I probably have more feathers or do I have more rocks?
More feathers.
I have more feathers. A mole of copper is like the feather, it weighs less. And the mole of gold is like the rock, it weighs more. Yeah.
I have a question back to, the math part. If you have a decimal, do you just round up or do you keep the decimal?
Or is it 6
You would,
Yeah, cause like for NaCl, that one comes out to like 57.49.
if the question specifically was, what is the molar mass?
Mm-hmm,
Sig figs wouldn't really play into it. There's no correct number of sig figs.
right.
Yeah. If you had to use this in a problem, then use enough sig figs that this doesn't determine the sig figs for your problem. So if the question said you had 2 grams of calcium chloride,
Mm-hmm.
how many sig figs are in 2 grams? Or there's 1 sig fig in 2 grams, okay? So just be sure to take this number past one sig fig. That way your 2 grams is what's determining your final answer.
Okay.
So we can do this math using dimensional analysis, okay? You can probably do this math without dimensional analysis at this point. But next week or the week after, we're going to get into something called stoichiometry. It's going to involve these same steps, but you are definitely going to want to do dimensional analysis there. So I would get in the habit of doing it here, okay? I do dimensional analysis even on this, okay? So do it. So if we want to convert grams of CO2 to moles, let's go back to our dimensional analysis. What's the very first thing I write when I'm doing dimensional analysis? This is the thing that I'm starting with, my starting point. What is my starting point? 10 grams of CO2. That's my starting point. Before I do anything, I can do this. What has to be my unit here?
Moles.
CO2.
Grams.
Grams of CO2. It has to cancel this.
Oh, okay.
This unit immediately goes there. Okay? So what is my ending unit? Where am I trying to get to?
Moles.
Moles. So let's put moles here. You're going to see, and I have it here, moles is shortened to mole. M-O-L. Okay? Same thing. But you're going to write this a whole lot of times, and you're going to be thankful you don't have to write ES every time. Okay? So, what relationship do we know between grams of CO2 and moles?
1 mole equals the mass of the element.
Right. 1 mole equals that number of grams. Okay? So what is the molar mass of CO2? 44.01. 1 carbon plus 2 oxygens comes out to be 44.01. So now, this cancels, I'm left with my final unit of moles. So all I have to do is the math. So remember, this is the other way of doing dimensional analysis. multiplying by these fractions. Same thing. So they took 10 grams, 1 mole on top, 44.01 grams on the bottom, equals 0.277 moles of CO2. We just converted between grams to moles. That's exactly how you will always do it. If you're going from grams to moles, grams, grams, moles, do the math. Do another one. How do I convert half a mole of CO2 to grams? Oh, let's go in the other direction. Half a mole of CO2 to grams. Yes, Beth.
About the last problem.
Mm-hmm.
Am I doing this wrong, or do you multiply the 10 by the 1 and then divide?
Yes. So now what it comes out to be?
I'm getting 0.227.
Yeah, you divide the 1 by 44.
Does everyone get 0.227?
Yep, I
Yeah.
got 0.227.
Okay, then that is correct. That's another typo. Thank you. We want to go the opposite direction. Dimensional analysis again. Where am I starting?
0.50 moles of CO2.
0.50 moles of CO2. Draw my grid. What's my unit here? Mole of CO2. What's my unit here?
Grams.
Grams of CO2. What number am I going to put here? 1 mole equals how many grams? 44.01. So now it just becomes half of that equals 22.005 grams, but I only have how many sig figs? 2. The 0.5 only has 2.50. So this becomes 22 grams of CO2. It's not hard. It's just like a conversion, like you're doing inches to centimeters. It's the same thing. You just have to remember your conversion factor is 1 mole is that many grams. Is that the same thing? Oh, it's oxygen. If I want to convert 10 grams of oxygen to moles, what am I going to do?
Start with 10 grams.
Alright, start with 10.0 grams of oxygen. What goes down here?
Grams of oxygen.
Grams of oxygen. What goes up here? Moles of oxygen. That's my number here. 1. What's the number here? 32. Each oxygen is 16. So 2 of them is 32. Becomes 10 divided by 32 is 0.312 moles of oxygen.
So,
What's sticking here?
so did we divide 10 by 32?
So what we did,
Okay, because you
here
were
we-
times
10
that and
times
not
1 on the top
Yeah, okay, see,
is 10,
okay,
and then we got nothing times 32 is 10 divided by 32.
that's right.
Now we can take this one step further. We can go between moles and particles. Because we can go from grams to moles, we can then go from grams to particles through moles, okay? There's gonna be a multi-step dimensional analysis. Remember, a mole is 6.022 times 10 to the 23rd particles. Meaning, when you do dimensional analysis, you can always have and 6.022 times 10 to the 23rd atoms or particles, or you can flip this you can do it either way. That is going to be your conversion factor for the last step. You just have to figure out which one you're going to use, and the dimensional analysis will tell you if you need to cancel the units. The question is, what mass of magnesium chloride contains 6.022 times 10 to the 23rd chloride ions? Okay. So, what do you think is our starting point here?
The mass of, magnesium.
We don't know that mass, though. We have to find it. So that's our ending point. What is our starting point?
6.022 times 10 to the 23rd.
Right. 6.022 times 10 to the 23rd chloride ions. So, without even thinking about what this relationship is, what has to be my unit here?
Chloride ion.
Chloride ions, right? What relationship can you come up with that includes chloride ions that's going to help us here?
Particles.
Relation
No.
right on
Sort of.
to magnesium chloride.
Yes. What we're trying to get to in the end is magnesium chloride. What we have here is just chloride. So we can say that there's a relationship between the number of chloride ions and magnesium chloride molecules. What is that relationship?
2 to 1.
For every magnesium chloride, there are 2 chlorines. 1 magnesium chloride, 2 chlorides. Those 2 things are equal to each other, so that's my next step. So then what has to be my unit here? Actually, let me go back. Because there are 2 chlorines for every magnesium chloride, that means there are 2 moles of chlorides for every 1 mole magnesium chloride. Okay. Does that make sense? I missed that part. Okay. So, now what has to be my unit here? Moles of magnesium chloride. And what can I put up here that's going to get us to our answer? Grams of magnesium chloride. What number is going to go here? 1. Now I have to figure out what number goes here. So it's magnesium, which is 24.3 plus 34.5. There's 2 of them. There's 2 chlorines. So you got. Somebody's telling me the answer. 95.2.
It wrote down 95.
It's gonna be something 3.3 at the end. So what is it?
93.3.
93.3 grams of magnesium chloride. So you've got, multiply everything at the top. multiply everything, the bottom's easy, and there's 2 on the bottom. Then you have to multiply that big number by 93.3. .8 0023
10 to the 25th.
10 to the 25th, and then when you divide that by
That's
2,
already divided.
that's already divided.
Yeah, my bad.
So that's
5.6 is
0.60046, 10 to the 25th. Divided by 2. Is that what everybody got? When you multiply 6.022 times 10 to the 23rd times 93.3.
And then I multiply it across. Alright, mine's wrong. Mine's off
Okay,
by.
5.618, that's what I've gotten.
So,
So both of mine are wrong. I did 93 instead of 93.3.
okay.
In my math.
So what is 6.022 times 10 to the 23rd times 93.3?
5.618.
5.618 times 10 to the 25th. And then on the bottom we have 2. 2.809
809.
times 10 to the 25th grams of magnesium chloride. Okay. Grams of magnesium chloride was our last unit. So that's canceled, 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 canceled. Oh, not that, it's canceled. There's their work. And they got,
Yeah, they got, that's where I got it.
oh, I got it. I got it. You missed a step.
Cause the,
So, here we have 2 moles of chloride, right? What has to be the unit here?
Moles of chloride.
Moles of chloride. We didn't have moles of chloride here. We had chloride, right? So, our starting point is 6.022 times 10 to the 23rd chloride ions, right? We need to get from that to moles of chloride. How can we do that here? This has to be here, right? So 1 mole of chloride ions.
What if he's just moving that to the bottom, like the 6.022?
Right. So how many chloride ions are in a mole of chloride ions? 6.022 times 10 to the 23rd. Now our units cancel. Right? Chloride cancels chloride. Moles of chloride cancels moles of chloride. Moles of magnesium chloride cancels moles of magnesium chloride.
so it's 93.3 divided by 2.
Right. So this mathematically cancels that. So you end up with 93.3 divided by 2.
That makes a lot more sense.
Yes, it does.
Because that'd be a lot of grams.
A lot of
Yeah,
grams.
yeah, how does it match the front lines area?
So you get 93.3 over,
So you don't
You're
have to
forgetting the
multiply by that time.
6.0.022.
where it's here is what there's one on top.
Oh, and
the
'cause it
same numbers on the
cancels
bottom.
completely?
It cancels completely.
Okay.
You could multiply this 93.3 times that number, then multiply
And it ends
2
up being canceled
times
out
that number,
anyway.
and it cancels itself
Okay.
out.
Okay.
Okay.
Got
If you
it.
did the math in its entirety, you would still get the same exact answer.
Ooh, the 93.3
That's the molar mass of magnesium chloride.
But that's, slide 91.1.
Well, for the magnesium, you do the 34.5, and you multiply by 10.
It's actually 35.4
That's fine, but I
though.
want to know what the two differences are.
It's actually 35.4, not 34.5. When we did the math for the magnesium chloride, you put 34.5, and it's actually 35.4. Which
Okay.
makes a slight difference, but that's why they got a different answer.
So,
So you're gonna be off by 3 for that.
24.3, 34.
No, it's 35.4.
So it should be 7.
Ah.
I'm gonna just make one.
That's really
And if I
95.1.
don't get one small part, I just count them.
Okay. Did everyone hear where I messed up
Yeah,
again?
yeah. This is the basic, but when you start adding all these steps, I just have a hard time.
Got it.
Okay. So our molar mass was wrong. So which makes this 90.
Should we start?
Yeah, let's start.
Scribble it out.
You want to do it again?
Yeah.
Mulligan?
Mulligan?
Is there one on the next slide? What's on the next slide? Is there another one of these?
Empirical and molecular formulas. Sorry.
Well, let's make one up.
I need.
So we just rounding that up, because I got 47.4. Are we just rounding that up?
Okay. Let's do 3.011 times 10 to the 23rd. I'm making something up. That's what
Oh.
So it's not a mole?
It's happening.
Oh, okay.
Yeah.
Yeah, we said.
He just aimed at me, so it's on the curveball.
So I'm in the process of making the question. Okay? I'm-
It's brain drain
So-
all over the board.
Let's do lithium. We're trying to get to grams of lithium bromide. Okay? We have 3.011 times 10 to the 23rd bromide ions. Okay? This is where we're starting. We're trying to get to grams of lithium bromide. Just like up there, we're starting with a large number of ions, trying to get to grams of the compound. Okay? So, what is my unit that's going to be here?
Bromide ion.
Bromide ion. And this is where we messed up last time. What is up here? It's not the moles. Lithium bromide. What is the relationship between number of bromide ions and lithium bromide molecules?
1 to 1.
There's one bromide ion in every one lithium bromide. Okay? let's say there's one bromide ion atom for one lithium bromide molecule. Okay? So, what is going to go here?
Lithium bromide molecule?
Lithium bromide molecules. What number is going, what unit's going to go here? Grams? No, we got one more step before we can go to grams. Moles. What is the relationship between number of lithium bromide molecules and moles of lithium bromide? There's 1 mole of lithium bromide has 6.022 times 10 to the 23rd lithium bromide molecules. Okay? Now we follow dimensional analysis. Moles of lithium bromide goes there. Now what can we put here? Grams. Grams of lithium bromide. Right? What number is going to go here? 1 mole of lithium bromide weighs what? You have 6.9. And bromide is 79.9.
86.8.
Did someone who did it on a calculator get the same number I did? Okay. 86.8. Now you multiply everything on top, multiply everything on the bottom, and what you end up with on the bottom is going to be 6.022 times 10 to the 23rd. What's on top? .61 times
10 to the 25th.
times 10 to the 25th.
Yeah.
Is that what everybody got? We don't want to make the same type of mistake again. 2.61 times 10 to the 25th. Is that your final answer? Okay. So then when you divide them, what do you get?
.34 times 10 to the 47. It's kind
You're
of weird.
dividing to subtract the powers.
Oh, yeah.
The way that I did it is that, seeing as we're dealing with half a mole goes into a whole mole twice, so it'll cancel out. So it'll be 86.8 divided by 2.
So it actually.
Is that why you put like,
There's a half a mole, you start with half a mole. You end up with a full mole down here in the bottom, it would cancel out, so you'd have a 2 on the bottom.
You're going to make yourself, on future problems, you're going to mess yourself up if you try to start doing that.
4.342 times 10 to the 24th.
What is 2.61 divided by 6.022? Forget the powers.
0.0433, so 4.33,
It's less than 1, so it's 0.43,
433.
let's say 3. It's 3 or 4, doesn't matter. When we multiply, when we divide, we're going to take that exponent, subtract that
So 10
one, times
to 2.
10 to the second. Okay? This is not correct scientific notation. So this becomes 4.33 times 10 to the 1, which is 4.33 grams of lithium bromide.
Would it be 43.3?
Yes. Now is it right?
Go with that.
And make sure you get some credit for that exam.
So the final answer is
43.3 grams, which makes sense the way you were looking at it. He said, clearly you have half a mole, so you take half of that, and half of that is that.
Is that right?
Right. But if you have weird numbers, say this was not half a mole, say that was 5.9 times 10 to the 28. Now you have to do that.
Yeah,
You have to do all of this.
It's obviously half a wall.
Do we have a quiz today?
Yes.
You might have forgotten about it if you didn't ask.
Next slide is moving on. Are there any questions?
No, I'm just gonna fail that.
The whole number
Easier.
over there again. The whole number is 6.052. Why did that go in there?
That is because we had to get from molecules to moles. Because we know the relationship between moles and grams. We don't know the relationship between molecules and grams. We had to go molecules to moles to grams. And so there are 6.022 times 10 to the 23rd molecules for each mole.
The molecules and that is really something.
In a mole, yeah. It's just, here we have a compound with molecules. Here we have ions, so it's atoms.
Each compound, so yes. All right.
So if you had this problem on a quiz, say next week, what would mess you up? Why?
And I assume once we figure out the back and forth, I think we'll be fine.
What back and forth?
It's just a lot of conversions.
It's a lot of conversions, yeah.
Remember the thing we did in the beginning of the school year, we all put on the screen, the words that remind us of chemistry?
Yeah.
Conversions. That's the one.
Conversion?
That's the one I put up there because I remember this.
Chemistry is now conversions.
There's only one way. Memorize how to go.
We'll move on. Email me. Do not just let this go, okay? You don't seem to know exactly what the sticking point is, so we can't really fix it at this point. When you do homework and you hit a sticking point, let me know, okay? The next concept is empirical formulas. This is sort of similar to that percent composition. So empirical formula is a chemical formula for a compound, but it is sort of an experimental number. It is not an actual number where you can count and say there are this many and this many. All it's going to be is a ratio. Okay? And so it's the simplest ratio of atoms in a compound. And you write them as the smallest whole number subscripts, meaning if you have something that can simplify it. And we've done that with our ionic compounds from as soon as we started those, right? It's not calcium 2, oxygen 2. Those 2's simplify in the CaO, okay? With ionic compounds, you always do that. And with molecular compounds, you don't simplify. If it is C2O2, you leave it, C2O2. With an empirical formula, you do simplify. So the first thing we're going to learn is how to calculate an empirical formula. And then after that, we're going to take that and calculate molecular formulas. The molecular formula gives the actual number of atoms in the compound. Just like C2O2, that means in every molecule, there's 2 carbons, 2 oxygens. But the empirical formula is just C1O1, meaning for every 1 carbon, there's 1 oxygen. But you don't really know the exact numbers at that point. So let's look at these 2 compounds. What would you say is the same between them? What is that ratio? In both cases, for every carbon, there is 1 hydrogen, right? So, what would you say is the empirical formula for this compound? CH. CH. You simplify it. The 6's become 1's. So the empirical formula for that is CH. What is the empirical formula for this one? CH. They both have the same empirical formula, which means they have the same ratio of carbon to hydrogen, but the molecular formulas are different. When you look at it at the molecule scale, this one, there are 6 carbons, 6 hydrogens. This one, there are 2 carbons, 2 hydrogens. What is the empirical formula for hydrogen peroxide, H2O2? HO. What is the empirical formula for water, H2O? H2O. You cannot simplify it. Right? So here are some other examples. Don't worry about these too much. Cyclopentane, the molecular formula is C5H10. You can simplify that to CH2. This one doesn't simplify as cleanly as C2H6. They're not both the same number. But here, they're both divisible by 5. So you can simplify it. The 5 becomes 1, 10 becomes 2. C6H12, CH2. C2H4, CH2. Very different molecular formulas, but they're all the same empirical formula. Hydrogen sulfide, the molecular formula is H2S. Like with water, you can't simplify that. So it's both the molecular formula and the empirical formula. Calcium chloride is an ionic compound, right? It's a metal in it. We said with ionic compounds, you always simplify, which means if you always simplify, you're always dealing with empirical formulas. There is no such thing as a molecular formula for an ionic compound. You would never say Ca2O2. Here's visually, we can figure out empirical formulas. What would you say is the empirical formula? Wow, that's really hard to see. That's really hard to count. That one goes there. It looks like these rows of the little ones, the oxygens, go with these rows of mercuries. If that's the case, what is the ratio of the mercury to the oxygen? 1 to 1. Okay? That one's hard to see. These are easier. Here's CH2Cl2. What is the empirical formula of that?
CHCl.
Well, I heard Yeah. Well, there's only 1 carbon. There's 2 hydrogens, 2 chlorines. So you can't simplify it. You can simplify the hydrogen and the chlorines, but there's a carbon attached to them. And there's only 1 of them. So the whole thing, you can't simplify. What about C6H3Cl3? C2HCl. They're all divisible by 3, so you get C2HCl. How about H2C2O4? HCO2. N2O4?
Wait, no, NO2.
NO2. Goes through by 2. NO2. CH3, CO2, H.
Stays. Doesn't change, it's the same.
Let's rearrange this a bit. How many carbons are in there?
Two.
There's 2. There's that one, and there's that one. So you have C2. How many hydrogens are there? There are 4. 3 and 1. 4 and 2 oxygen. So, what is our empirical formula? CH2O.
Trick question.
N2H4, NH2, C2H6, CH3, CH2, CH2, CH3. So how many carbons? 3. How many hydrogens? 6. How many? That's it. C3H6 becomes CH2. And our last one is this weird looking thing, P4O6. P4O6 becomes P2O3. Does everybody see that one? That's the trickiest one. Divide
That's the
2 into both of
trickiest
them. What?
So that's the trickiest one.
Mathematically, it's harder. You just have to catch the random C in the middle of that. We can figure out these empirical formulas from numbers. Not just by looking at them or being given a molecular formula. We're going to go back to our chalcopyrite. Here's our chalcopyrite. This is the percent composition of chalcopyrite that we figured out. Let's figure out the empirical formula. The first step is, if you're given percents, make the math easy on yourself and assume you have 100 grams. Okay? If you assume you have 100 grams, then the percents for all the other things can just become grams. And you save yourself math. For each element, convert each of those grams into moles, and then take the smallest number of moles that you get. We're going to do this. We're going to do it. Take the smallest number of moles and divide that into all of them. What's going to happen is most of the time when you do that, you're going to end up with all whole numbers. And when you do, those whole numbers become your subscripts in your empirical formula. So, if we have 100 grams of chalcopyrite, just based on our percentages, we have that many grams of iron, copper, and sulfur. Does everybody see that first step? Okay. So the second step is to convert all of these grams into moles. So let's convert 30.5 grams of iron into moles. What's the molar mass of iron?
6.022 grams.
Molar mass is just the number from off. 55, let's go say 55.8. What is 30.5 divided by 55.8? 30.5 divided by 55.8.
0.546.
546 mole. Okay? Now we do the same thing for copper. 34.6 grams of copper grams of copper, 1 mole copper. What is the molar mass of copper? 63.5. 63.5. What is 34.6 divided by 63.5?
0.544.
0.544 mole. Same thing for sulfur. 34.9 grams of sulfur. 1 mole sulfur. What's the molar mass of sulfur? 32.1. 32.1. What is this?
1.087.
0.087 mole. Okay. That's the second step. Third step was to pick the smallest one and divide it into all of them. What's my smallest one?
Copper.
Copper. 0.544. Okay. If I divide that by this, by 0.544, it's going to be very, very, very close to 1. Okay? In this case, very close to 1 is 1. These numbers are experimental numbers. You know from lab, you don't get the exact number, right? If you weigh 5 grams of something out and put it on another balance, it's probably not even going to say 5 grams. There's experimental error. If you get something that comes out to be very, very close to 1, you treat it and you assume that it's a 1. Okay? So this becomes a 1. Does everybody see that? .546 divided by 0.544. That's the smallest one. I'm going to divide that number by that, and that is roughly 1. Very close to 1. We're going to call it 1. If I divide this by 0.544, what do I get? Exactly 1. If I take this, 1.087, divide by 0.544, what do I get?
About 2.
About 2. These are all whole numbers, so we're done. Okay? So this was iron. We take iron, it's a 1, so there's no subscript. Second one is copper, it's a 1, so there's no subscript. The last one is sulfur, it's 2, so the subscript is 2. So our empirical formula is that. This is a flow chart. We're not going to go through it. If it helps you, use it. Okay? I think we'll finish empirical formula and then we'll take a break. We'll go on to molecular formula. Here is another example. We have another mineral called cobalt. It has a percent composition of 66.5% of copper, 33.5% of sulfur. We have to find the empirical formula. What is the first step?
Convert the moles.
Change it to grams.
Change it to grams. If we assume there are 100 grams, then we know how many grams of copper and sulfur there are, right? Then we can convert that to moles. You are doing that little conversion in your head, and you're not even realizing you're doing it. But up here, we have to do it, okay? So 66.5% copper becomes 66.5 grams of copper. Copper, 1 mole of copper. What was copper? 63.5. What does that come up to be? 1.05?
Rounded, yeah.
Okay.
It's right there, number 29.
And then we have 33.5 grams of sulfur. Sulfur, or mole sulfur, sulfur was 32.1 equals
1.04.
1.04 moles of sulfur. What's the next step? Divide by the smallest one, which is what one? 1.04. If you divide this by 1.04, you're going to get 1. By that by 1.04, you're going to get about 1. And so what is our empirical formula? CUS. Okay. We're not going to do a whole problem like this. If you want to, we can do it during break. But let's say we did this problem. And instead of getting 1 and 1, say we got a 1.5 and a 2. We can't have decimals in our subscript. What do you think we need to do?
Round.
We can't round. That 1.5, that means there's 1.5 coppers for every 2 sulfurs. If we change that to 2, that is not the same. Then that's saying there's 2 for 2.
And would you multiply to get a whole number?
So you have to, right. So what can you multiply that by to get it to a whole number?
2.
2. So you can make that
3
3.
and
Multiply
4.
it by 2 to get 3. Then you have to multiply that by 2 also. So then that becomes 4. Okay? So when you divide, when you get these numbers, look and see if something strikes you as that's a convenient number. 1.5, 1.25, or 0.75, something like that. That's a clue that that's not a measurement error. That's something I need to multiply by. Okay? So let us take a break. And we'll start at 1/4 on this clock.
Pull it out.